So I was just, stumbling on the internet, just trying to find some math problems. I just thought that might be interesting to put it out on a video. And I actually stumbled across this this problem from the textbook, specifically Walter Rudin's Principle of Mathematical Analysis, covering this textbook problem specifically covering about the Riemann-Stieltjes integral. And so yeah, what we have is define f of x equals the integral from x to x plus 1 of sine of t squared dt, and prove that the absolute value of f of x is strictly less than 1 over x if x is greater than 0. And this problem actually has split into several parts, but this is only one part A of it. It's only one of the 4 sections to show. But we're just only going to show this section because the other problems have the other sections do things a little bit differently relating with this. So, all right, with that, let's actually get started. So, first thing we want to observe is f of x is equal to this integral, and we want to show that the absolute value of f of x is less than 1 over x. But we want to know what exactly the evaluation of this integral is equal to. So that's the first thing we're going to do. So first thing that you want to observe is when you're proving integrals such as this, your first thoughts, especially if you're taking from a Calc 2 class or even high school calculus, you want to your first thoughts might be thinking, why don't we try to use substitution? So let's actually try that. So we're gonna let u equals t squared. So let u equals t squared, and then use substitution, take the derivatives of both sides, respect du and then dt. So du is equal to the derivative of t squared 2t times dt. And notice that we want dt by itself, so when we do the substitution, integrating it with a different variable will make things a little bit easier for us. Note that if we were to substitute like this, we don't have anything to cancel because there's no 2t inside this for it to cancel out to do the substitution in respect to u. So what we can do is we can actually, and we want dt by itself to do the substitution, as I said already. So we can divide this by both sides by 2t, so du is divided by 2t is equal to dt. But we have our dt, but don't forget we have our u and a t, but we want everything in this side to be all variables of u. So we can actually replace this t with a u variable. We have that u is equal to 2t, so we get t by itself. We take the square root of both sides, so we get the square root of t is equal to the square root of u. So this would mean du is equal to 2 times the square divided by 2 times square root of u is equal to dt. And now we have that. We have one variable on the other side, on one side and the other, we can do the substitution right here. And don't forget, because we have x and x plus 1, when you're doing substitutions, you have to always change your bounds as well with the variable you're integrating in respect to. So in this case, we have that u is equal to t squared. We have that u is equal to x and then u is equal to x plus 1. You just plug x into the formula here, same thing for x plus 1 into here. So that we have our new bounds as u is equal x squared all the way up to u is equal to x plus 1 square, in the x plus 1 parentheses then square. So let's do that. We have this, oops, I wrote. We have the integral of x squared x plus 1 square of sine of the t squared is equal to u, so sine of u, and then replace our dt, so du divided by 2 times square root of u. So we write that as this square x plus 1 square of sine u divided by 2 square u du. Okay. So now that we have that, now integrating this will be a little bit easier. But how would you integrate this? Another integration method is using integration by parts. which is taking the antiderivative that originally yields from the product rule when you do differentiation. So integration by parts formulas by parts. Its formula is, and because I already use u in this case, I'm going to use different variables. So we're just going to call it v times w minus the integral of w dv. Meaning, when we have this, we want to choose our v from here so that we take the derivative of it, we get our dv, and then when we choose our dw, TV show from our character for Arthur, by the way. When we choose our dw, we integrate that to get our w function. So let's choose v. Let's actually choose v to equal v is equal to 1 over 2 times the square root of u d. Actually, no, not d. Not yet, because we have to take the derivative of that first. Or let's rewrite this as exponent rules. We have 1 over 2 times u times negative half exponent rules. So we take the derivative of this. We have dv is equal to negative 1 over 4 u minus 1, so negative 3 over 2 du. And then choose our dw to integrate. dw, we're going to let that be equal to sine u du, and then w is equal to negative cosine of u. Now that we have all the pieces here, let's actually multiply with the terms together for the integration by parts. V times w minus the integral of w dv. So in this case, we would have negative cosine of u divided by 2 divided by u from x plus 1 squared to x squared minus the integral of x squared and x plus 1 squared of w times dv. So negative times negative positive, so this sign will still retain. So this will be cosine of u divided by, and I'm going to rewrite the exponent on the bottom, so divided by 4 u times 3 over 2 du. Now, we could integrate this if we want to, but it repeats. So you would have to continuously do integration by parts over and over and over and over because it's a cosine function. The same thing would apply for sine functions too. The cycle repeats, like it's ongoing. So we're not going to do that because that's just going to take forever. So we're just going to leave the integral as it is, and now we'll just evaluate our bounds from here. So plug in here. So we have negative cosine of x plus 1 square divided by, plug the x plus 1 square into here, square and square root cancel out, so it'll just be 2 times x plus 1, then minus, so this will be a plus cosine of x squared divided by, same thing as before, x squared, so they cancel out with the square root, so 2 times x, and then minus integral of x squared, x plus 1 square, cosine of u divided by 4u 3 over 2 du. And like I said, we can continue to integrate this if we want to, but it's just going to keep repeating. You have to constantly repeating, doing integration by parts over and over until there's like no integrals, but it's going to go on forever. So like I said, we're just going to leave it as that. So now that we have this, I'm going to actually put this term into the front so that the leading is positive. So this will be cosine of x squared divided by 2x minus cosine of x plus 1 square divided by 2 times x plus 1 minus from x squared, x plus 1 square, cosine u 4u 3 over 2 du, and we're going to let that equal f of x, because that's all we can do for now. Now that we have the f of x, now that we evaluate what f of x is equal to from here, now we can actually get to the actual proof to show that the absolute value f of x is strictly less than 1 over x for every x greater than 0. So let's get on a roll with it. So rewrite this absolute value of f of x and equal to this cosine of x squared 2x minus cosine x plus 1 squared divided by 2x plus 1 minus the integral from x squared to x plus 1 squared cosine of u 4 times u to the 3 over 2 du. That. Alright. Now that we have this, but now the thing is, we actually want to get an inequality so that we can actually prove this statement right here. So how do we get from an equal sign to get to some form of inequality? Well, what we can do is actually use triangle inequality, as we have the absolute values, and we can actually split each of the terms into its own absolute value form. And because absolute values are positive, we can actually just change these negatives to just positive. So we can change that so it's less than or equal to cosine x squared divided by 2x plus cosine of x plus 1 squared divided by 2 times x plus 1, then plus the integral of x squared x plus 1 squared cosine of u divided by 4 times 3 over 2 du. Okay, we have this, but now take a look at this inequality. Less than or equal to. But what we want to achieve is the absolute value of f of x is strictly less than 1 over x. But how do we do that? That's the next question. Well, take a look at this. Here's an observation that you want to take a look at. We have a cosine x squared, a cosine x plus 1 squared, and a cosine u. Now, the cosine function is actually a bounded function, meaning the function oscillates, and it can only go it oscillates between from positive 1 to negative 1. Its minimum will always be a negative 1, and then its positive will be a 1, positive 1. It doesn't matter the input inside, cosine functions will always be bounded between negative 1 to 1. And you can actually verify this yourself by graphing these equations here, and you can take a look at these functions. The highest f of x value it'll ever attain is at 1, and then the lowest will be at negative 1. But because we're dealing with absolute values here, we're only focusing on positive, strictly positive numbers. So the highest we can say is 1. And so because cosine of u, or cosine like of any of these functions, is less than or equal to 1. But because this is not a constant function, we can now argue and say that it's the cosine of u is strictly less than 1. So now that we can actually change the inequality to strictly less than, but it could be at most 1. So we can actually replace all these cosines over here with just 1. So replace cosine x squared with 1, cosine x plus 1 squared 1, and then cosine u 1. So that's the aim here. Plus this. Then plus right here, and then integral of x squared x plus 1 squared 1 divided by 4. So now would you look at this? This is now actually easier to compute. We don't even have to do integration by part. You have to do integration by parts with this, but then it just repeats, but that'll just make our lives even more miserable if we do try to evaluate this definite integral. Now that we have this is actually a lot easier to integrate now. So I'm gonna show my work on this side here to evaluate this integral right here. So we have, all right, x squared, then x plus 1 squared from 1 over 4 u 3 over 2 du. And I can take out the 1 over 4, it's a constant, move it outside the integral, and I'm going to change this 1 over u to 3 over 2 as a negative exponent, so it would be 1 over 4 times the integral of x squared, then x plus 1 square of u negative 3 over 2 du, and then power rules, so u negative 3 over 2 plus 1 divided by negative 3 over 2 plus 1. This will be equal to 1 over 4 negative 2 negative 2 times u to negative 1/2, so I'll just write as negative 2 divided by the square root of u from x plus 1 squared to x squared. Then here is still 1 over 4. Then have negative 2, just like before, x plus 1 squared, put it into the square root, squares cancel out, so it'll just be x plus 1, then minus minus, so that's a positive 2 divided by x. And then multiplied, we can actually factor out the negative 2, so it'll just be negative 1/2 times 1 over x plus 1 minus 1 over x. And then I'm gonna simplify this out so we get a common denominator. So this will be negative 1/2. Okay, this should be, okay, let me see. X plus 1 and times x, common denominators, so go do that. Minus x plus 1. Okay, so cross multiply, so this should be a x over here, and then this should be a x plus 1. Then this will be negative 1/2 times x minus x is 0, then minus positive 1, negative 1 divided by x plus 1. And then we get multiply the constant into here, so this will be positive 1 divided by 2 times x plus 1. This is equal to this. So we are going to replace that now, which is equal to 1 over 2x plus 1 over 2x plus 1, and then plus 1 over 2x plus 1 right here. And all positives, take out the absolute value, equals 1 over 2x plus 1 2x plus 1 plus 1 2x x plus 1. Okay, and now let's just now we can actually get the common denominator, multiply x here, multiply x plus 1. I just realized my camera just looks, is it right? Yeah, okay, that's fine. So now we have x plus 1, okay, equals, okay, I'm gonna write everything into common denominator, so this should be 2x x plus 1 over here, 2x x plus 1, 2x, whoops, 2x x plus 1. Okay, so all our common denominators, this will still be 1. Multiply x here, so this should be x. Multiply over here, this should be x plus 1. And so we have, okay, x plus x, 2x and 2. Okay, and then 2x plus 2, factor out the 2. So 2x plus 1 all over 2x, x plus 1. Cancel out. We have 2 divided by 2x, it is equal to 1 over x, like so. This whole thing here that we evaluated is equal to 1 over x. We showed that the absolute value f of x is strictly less than 1 over x for all x greater than 0. So now we can conclude that the absolute value of f of x is strictly less than 1 over x for all x greater than 0. And there you have it. Oh, wow. Wow, I'm out of breath. Oh, this video took 20 something minutes just doing that. Wow. I don't know why it's bothering me. I thought like my camera looks off, but it's probably me just hallucinating. But interesting problem. A lot of analyzing with the cosine functions, with the boundness to change the inequality. Straight up just computation, you know, stuff like that's what I like. Evaluation from getting this, and then once you have that, show absolute value f of x strictly less than 1. You do all this work and then come to the conclusion with this. Sweet. So, wow, I have not made a video in 2 weeks, so thank God I did this. So, thank you guys for watching. Come check out I just dropped my marker. Feel free to leave a like, comment, subscribe to the channel if you're new. I just did, actually did some proofs on the differentiation rules, the basic differentiation rules. You should check that out. And there's also a math playlist if you want to check those out too. So that'll be it. Thank you for watching. And you know, I just came home from basketball and my legs are just so messed up. And you want to know the funny thing is, I'm still going to play basketball tomorrow. So here's hoping I don't run out of breath.